So we can also look at collisions that happen between objects now that are more rigid. So for example, let's say we have a stick and it's floating in space. Okay, so it's not interacting gravitationally with anything. And so it's uniform density, so it has its center of mass in the middle. And then we'll say that we have like a piece of clay that's flying through space with some initial velocity v. And we'll say that the length of the stick is d. And we'll say that after some time, the clay is going to come and it's going to hit the stick and it's going to stick to it. And it's going to be some distance, little d, from the center of mass of the stick. Okay? So we know that when this happens, this is going to start to rotate, right? And it's also going to be moving. So it's going to be rotating, and it's also going to be moving horizontally. So first, let's find out what the speed of its rotation is going to be. So to do that, we'll use the conservation of momentum. So initially, it's the mass of the clay times d, right, at this distance, times its velocity. And if you're wondering why that is, remember again that we can call this r, and since L is equal to r cross p, this is just r p sine theta, where theta is this angle, and again r sine theta is just this d. So we can write L as the mass of the clay, v, this is the momentum part, and then r is the d. Okay, but afterwards, right, momentum's conserved, so that's the same thing as the mass of the clay times d times v final, plus the moment of inertia of the rod times omega final. And so we see that this is the mass of the clay times d times v final plus the moment of inertia, which is mass of the rod divided by 12 times r squared. Actually, sorry, we don't even need to do, so mass of the omega times r squared times omega f, and r squared in this case is d, so we could have substituted that in here. This is d. So we see that omega final is mass of the clay, d, times its initial velocity, divided by mass of the clay, d squared, plus mass of the rod over 12, big D squared. Okay, and so the way I got this term, remember, is that velocity is equal to omega final times its distance from the point of rotation, which in this case is d. So that's where we got the other d here for the d squared. So this is the rotational speed of the system. Okay, but remember, there's also going to be a transverse speed, because this is moving, so we also conserve linear momentum, right? And so if we want to look at what the linear momentum is, we say, well, initially the momentum was the mass times v 0, right? So it was all in the x direction. This is the mass of the clay. And then finally, this is going to be the mass of the clay, v final 0, plus the mass of the rod, v final 0. So in other words, v final as a vector is just the mass of the clay over the mass of the clay plus the mass of the rod times v 0, right? And so this is exactly what we would have gotten if we just had two particles and one of them came and collided and hit the other, right? So our final velocity for the system's the same. The only difference is now we also have a rotation that's going along with it. So you can expect to see some of these types of questions on your exam, and even on like the final exam for the class.